Welcome back to the deep dive. Today, we are rewinding the clock a bit to May 2023.
Which, in AI years feels like an absolute century ago.
It really does. But it's this incredibly crucial moment that challenged what I like to call the Goliath narrative of artificial intelligence.
Right, that pervasive idea that AI is purely a game of massive resources.
Exactly, the moat theory.
Yeah.
This assumption that whoever have the biggest data set or the most GPUs and just billions of dollars to burn on electricity is the only one who even gets a seat at the table.
And that if you don't have a spare 10 million for a compute cluster, you just can't play.
Right. But today we are breaking down a paper that looked right at that massive barrier to entry and basically said, we can get around that.
Yeah.
We are talking about QLoRA. That's efficient fine-tuning of quantized LLMs by Tim Detmers and his team at the University of Washington.
I mean, this is basically a foundational text for the open source AI movement. If you are running a high-performance model on your laptop today, or, if you're using any of those thousands of fine-tunes on Hugging Face, you probably have this specific paper to thank for it.
And the numbers alone really set the stage for why this was such a big deal. We are talking about fine-tuning a massive model, specifically 65 billion parameters.
Yeah, the LLaMA 65B.
Right. And in early 2023, doing that usually required a whole cluster of high-end industrial GPUs. We're talking hundreds and hundreds of gigabytes of VRAM. But these researchers, they pulled it off on a single 48 gigabyte card.
Which is just, it's staggering to think about. They took a task that was exclusively the domain of massive tech giants, and they compressed it down into a single workstation.
Yeah.
They basically crammed a supercomputer task onto what is essentially a high-end gaming rig.
So the mission for this deep dive is to really understand the mechanics of this magic trick. How do you fit a whale into a goldfish bowl?
I like that analogy.
And more importantly, and this is something I really want to push back on a bit later, did it actually work? Or was it just a parlor trick? Did they sacrifice the model's intelligence for the sake of efficiency?
Well, the spoiler alert, and really the whole reason we're still talking about this paper today, is that they claim they didn't. They claim to have democratized access to state-of-the-art AI without losing task performance.
Democratizing is a big word. So let's strip it back. Before we get into their solution, I want to physically understand the problem.
Okay.
Let's say it's 2023. I'm a researcher. I managed to get my hands on the LLaMA 65B model weights. Why can't I just train it on my home rig? What is actually happening inside the GPU memory?
So it all comes down to the fundamental difference between running a model and training a model.
Okay.
If you just want to run inference, if you just want to ask the chatbot a question, you only need to load the weights. But for a 65 billion parameter model at standard 16-bit precision, that alone is about 130 gigabytes of memory.
Right. So I'm already out of memory on a consumer card just trying to turn the thing on. Exactly.
Because the best consumer cards usually top out at, 24 gigs, and prosumer cards are at 48.
Yep. But training is exponentially worse. When you fine-tune a model, you aren't just reading those weights, you are actively updating them.
Right, you're changing the brain.
Exactly. So you need to store the gradients, which are the calculated errors, and you need to store the optimizer states. Standard algorithms, like Adam, for example, they stored 2 extra states for every single parameter just to help it learn smoothly.
Wait, so for every single parameter, you're storing the weight itself, the gradient, and 2 optimizer states?
Precisely. So the memory requirement just completely balloons.
Yeah.
For a 65B model, doing standard 16-bit fine-tuning would require more than 780 gigabytes of GPU memory.
780 gigabytes.
Yeah.
And the card they use for this paper, the NVIDIA A6000, that only has 48.
Right. To get 780 gigs, you'd need a rack of something like 16 of those A6000s all networked together. That's tens of thousands of dollars just in hardware.
Wow.
It was a complete non-starter for basically 99% of the research community. So enter QLoRA. Now, we have covered LoRa in previous deep dives. Low-rank adapters. That's the concept where instead of retraining the entire 65 billion parameter brain, you freeze the base brain and just train a tiny little adapter layer on top of it.
Right.
It's kind of like adding a new skill chip to a robot instead of rewiring the whole robot.
That's a great way to put it. And LoRa was step 1. It drastically reduced the number of parameters you actually had to train. But here is the catch.
Okay.
Even with LoRa, you still had to load that massive base model into memory at 16-bit precision just to generate the signals to train the adapter.
Oh, I see. So the robot is still too big to fit in the room, even if you're only trying to fix its hat.
Exactly. Perfect analogy. And that is exactly where the Q in QLoRA comes into play, quantization. To fit the model into the GPU, they had to shrink the base model down.
Right.
And they didn't just go down to 8-bit precision, they went all the way down to 4-bit precision.
Yeah. Now, 4-bit sounds incredibly lossy.
Uh.
I mean, if I take a high-res photo and crush it down that much, it turns into pixelated garbage. Usually in computing, if you reduce the precision, you severely reduce the accuracy. How does this not just destroy the model's intelligence?
Well, that is the general rule, but Detmers and his team found a way to backpropagate gradients, which are essentially the learning signals, through a frozen 4-bit quantized base model directly into those high-resolution adapters.
So the base is low-res, but the actual learning is happening in high-res.
You nailed it. The base model is frozen in 4-bit, but the adapters themselves are kept in standard 16-bit B-float.
Okay.
The real aha moment of this paper was mathematically proving that you can mix these precisions and still get a model that learns just as well as if you had used the massive, expensive hardware.
Okay, but you can't just indiscriminately chop off the decimal points and, hope for the best.
No, definitely not.
The paper mentions 3 specific technical innovations that make this possible. And I want to go through these carefully because this is where the actual engineering genius lies. It isn't just one magic trick, it's a stack of 3 distinct tricks.
It really is a masterclass in optimization. They attacked this memory bottleneck from 3 entirely different angles simultaneously.
All right, so let's start with the first one. It's a new data type they called 4-bit NormalFloat, or NF4. Now, I know what a float is. I know what 4-bit means. But NormalFloat, why do we need a special custom type of number for this?
This part is really cool. You have to think about the weights inside a neural network. They aren't just random numbers scattered evenly everywhere.
Right.
They tend to follow a very predictable normal distribution.
Like a bell curve.
Exactly like a bell curve. Most of the weights are clustered right in the middle, very close to 0, and very few of them are way out at the extreme edges.
Okay.
The problem with standard 4-bit quantization, what we would call integer quantization, is that it creates evenly spaced bins for the numbers.
Like marks on a ruler. Maybe every inch.
Exactly. But your actual data isn't spread out evenly like a ruler. It's all piled up right in the middle. So if you use a standard ruler to measure it, you might have one bin trying to hold that huge pile of data in the center, and then a bunch of bins out on the edges that are basically totally empty.
Oh, I get it. You are wasting your precious 4 bits on empty space.
Yeah.
You're optimizing for the outliers instead of the actual bulk of the data.
Precisely. So NF4, the 4-bit NormalFloat, the authors describe it as being information theoretically optimal. They mathematically calculated the exact shape of that bell curve and designed the data type to match it perfectly.
So the bins aren't evenly spaced anymore.
No. The bins are tiny and tightly clustered right in the middle where all the data actually lives, and then they get much wider out at the edges where there's barely any data.
It's kind of like zoning a city. You put small, dense apartment buildings downtown where everyone wants to live, and then huge, sprawling farm lots out in the countryside.
That is a fantastic way to visualize it. By matching the data type directly to the natural distribution of the weights, they drastically minimize the error when they compress it. They fit more actual information into those 4 bits than anyone previously thought was possible.
So they aren't just blindly compressing. They are compressing intelligently based on the specific shape of the brain they are scanning.
Correct. And that is exactly why the performance doesn't immediately degrade into that pixelated image you mentioned earlier. They preserve the detail exactly where it mattered most.
Okay, that makes sense. So we have a better, smarter suitcase for our data. That brings us to innovation number 2, double quantization. Now, this just sounds like Inception to me. We are quantizing the quantization.
We really are. And to explain why, we have to look at how quantization actually gets applied in practice. You don't just compress the whole 65 billion parameter model all at once in one big go.
You don't.
No, you do it in very small blocks, usually something like 64 parameters at a time.
Why do it in blocks? Why not just do the whole thing and be done with it?
Because if you do the whole thing at once, a few extreme outlier numbers will skew the entire map.
Ah.
By doing it in very small blocks, you keep the compression local and highly accurate. You check the range of numbers just in that tiny block, and you create a scaling constant, a sort of reference number, for just that block.
Okay, I follow. So every little block of 64 parameters has its own unique decoder key or constant attached to it.
Right. And those scaling constants are usually standard 32-bit numbers. Now, one 32-bit number doesn't sound like much overhead, but when you have 65 billion parameters...
You have over 1 billion constants.
Exactly. And those constants start eating up massive amounts of memory all on their own. The researchers actually calculated that just storing these constants was taking up multiple gigabytes of VRAM. It was this hidden massive cost of quantization.
So double quantization is what? Compressing those decoder keys?
Yes. They treat those quantization constants as if they were just new input data, and they quantize them again, crunching them down from 32-bit to 8-bit.
That feels really risky to me. At some point, don't you just lose the actual signal? If you compress the data and then you compress the key, you need to unlock the data.
You would definitely think so. It sounds incredibly dangerous. But they mathematically proved and showed in their tests that by doing the second layer of quantization, they saved an average of 0.37 bits per parameter with zero degradation in the final task performance.
1.37 bits. That sounds laughable. Why do we even care about a fraction of a single bit?
Well, pull out your calculator and multiply 0.37 by 65 billion.
Oh.
Yeah. You've just instantly freed up about 3 full gigabytes of GPU memory.
3 gigabytes. Okay, in the world of trying to squeeze onto a single GPU, that is significant. That's the difference between being able to run a batch size of 1 and a batch size of 4, or, fitting a much longer context window for the user prompt.
Exactly. It's about scraping the barrel for absolutely every single ounce of efficiency. It's what ultimately allowed them to fit the 65B model onto that 48 gigabyte card with enough room to spare for the gradients to actually do the training. It turned what was barely impossible into just barely possible.
That is incredible. It's like extreme couponing, but for VRAM.
Totally.
All right, so innovation number 3, paged optimizers. Now, this one sounds less like complex math and more like straight-up operating system management.
It is. It's borrowing a classic trick that CPUs have used for literally decades: paging.
So explain the specific problem this solves. Because we've already squeezed the modder down with NF4, we've squeezed the constants with double quantization. Why do we still need another safety net?
Because the training process is volatile. When you are fine-tuning a model, memory usage is not a steady flat line. It constantly spikes up and down. Maybe your batch of training data happens to hit a really long, complex sentence, and suddenly the activation memory just explodes for a second.
And usually when that sudden spike hits the hard physical limit of your GPU RAM.
Boom. You get an ORM error. Out of memory.
The worst.
The absolute worst. The entire training run crashes, you potentially lose your progress, or you have to completely restart from scratch with a smaller batch size. It is the bane of every AI researcher's existence. It effectively means you always have to leave a huge, wasteful safety buffer of unused memory just in case a spike happens.
So how does the page optimizer actually fix that?
It utilizes the unified memory feature that's built into NVIDIA GPUs. It basically treats the GPU memory and the CPU RAM like your regular system memory as one giant single pool of memory. If a sudden spike happens and the GPU is completely full, it automatically pages some of the optimizer states out to the much slower CPU RAM.
It's basically an overflow parking lot.
Exactly. Now, moving data back and forth over the PCIe bus, the physical connection between the GPU and the CPU is very slow compared to just keeping it on the GPU. But these memory spikes are rare and brief, so maybe your training slows down for a split second while it shuffles the cars around in the parking lot. But the crucial thing is it doesn't crash.
So it deliberately sacrifices a tiny, tiny bit of speed to guarantee stability.
And because of that stability, it allows you to train right up against the red line. You don't have to leave 10 gigabytes of memory totally empty as a safety buffer anymore.
Yeah.
You can use all of it, knowing the paged optimizer is there to catch you if you fall.
Okay, so let's recap this stack before we move on. We have NF4, which is finding the mathematically optimal data shape. We have double quantization, which is compressing the constants to save 3 gigs. And we have paged optimizers, the overflow safety net.
Right.
And they put all this together, and they didn't just stop at writing a theoretical paper. They actually built a model to prove it works. And they called it Guanaco.
Guanaco. Keeping nicely with the whole LLaMA theme that was going on, it's a smaller, more agile relative of the LLaMA.
And this is really where the rubber meets the road for me.
Yeah.
Because you can have all the fancy, elegant compression algorithms in the world, but if the resulting model is dumb, none of it matters. So how good was Guanaco actually?
This was the part that sent a shockwave through the community. They fine-tuned this model on a dataset called OASST1. That's the Open Assistant dataset. And when they tested Guanaco on the Vicuna benchmark, it outperformed all previous openly released models. Every single one.
But the headline number, the one that got everyone on AI Twitter screaming at the time, was a direct comparison to ChatGPT.
Right. They claimed that the Guanaco 65B model reached 99.3% of the performance level of ChatGPT.
Okay, 99.3%. I have to stop you there. That sounds highly convenient. You're telling me a model trained in 24 hours on one single graphics card is basically perfectly identical to the most expensive compute-heavy AI in human history. That feels like pure marketing fluff. How can that possibly be real?
It definitely sounds too good to be true. And we do need to unpack that specific number because it was heavily debated. But first, we should just appreciate the sheer efficiency gain. Even if 99.3% is a slight exaggeration, the fact that a single GPU model is even in the same conversation as ChatGPT is wild.
That's true. 24 hours of training versus literally months of data center training.
Right. And they didn't just run one lucky test and publish it. The paper details that they used this QLoRA method to fine-tune more than 1,000 different models.
1,000?
Over 1,000. They tested across 8 different instruction data sets. They used different model architectures like T5 and LLaMA, and they scaled it all the way up to 65 billion parameters. So the methodology itself is incredibly robust. But let's talk about that 99.3% claim.
Yes, let's. Because we all know AI benchmarks are notoriously messy and easy to game. How do they actually measure that 99.3%?
This is actually one of the most fascinating and insightful parts of the whole paper. The authors are incredibly open about what they call the evaluation problem. They basically found that the standard automated benchmarks available at the time just weren't trustworthy anymore. They didn't reflect how a human actually feels when talking to a chatbot.
Right, getting a high score on a multiple choice test doesn't mean the bot is actually helpful in a conversation. So they couldn't trust the automated code, and I assume they couldn't afford to hire thousands of humans to subjectively rate every single response.
Exactly. So they used GPT-4.
Wait, they used their main competitor to grade their own homework.
They did. They set up a system where GPT-4 acted as an automated judge. They would show GPT-4 a prompt, then show it the response generated by Guanaco and the response generated by ChatGPT, and then they would ask GPT-4 to rate them both out of 10 or to declare a winner.
Is that actually reliable? I mean, isn't there a massive risk that GPT-4 naturally prefers answers that sound exactly like itself? Or that it's just inherently biased towards really long, wordy answers?
There absolutely is a bias there. And the AI community has debated this whole LLM as a judge concept endlessly since this paper came out. But Detmer's team found that GPT-4 evaluations were a, quote, cheap and reasonable alternative to human evaluation. Because when they did do spot checks with human graders, the GPT-4 rankings correlated pretty closely with what the humans thought.
Fair enough. I know it's pretty standard industry practice now, but back in May 2023, that was quite a novel approach. But the authors did something else in their evaluation that I deeply respected.
Yeah.
They didn't just show us the high scores and walk away. They did what they called a lemon-picked analysis.
Yes.
I absolutely love this term. Usually in AI marketing, companies do cherry picking. They only show you the absolute best, most mind-blowing examples. Look, our bot just wrote a flawless Shakespearean sonnet about quantum physics.
Exactly. Lemon picking is the exact opposite of that. The researchers specifically looked for and then prominently demonstrated the cases where Guanaco completely failed compared to ChatGPT. They actively wanted to be transparent about the model's limitations.
Which is such a breath of fresh air in this industry. So what kind of lemons did they actually find? Where does that whole 99.3% illusion start to break down?
Well, despite the incredibly high conversational and instruction-following scores, they showed that the quantized model really struggled with things like complex mathematical reasoning or deep coding logic.
Okay.
If you asked it a tricky, multi-step logic puzzle, the effects of the heavy quantization and the fact that it didn't have the massive pre-training depth of GPT-4 would immediately start to show through.
So it's essentially a really smooth talker, but maybe not a particularly deep thinker when push comes to shove?
In certain domains, yeah, absolutely. They also noted it could hallucinate facts, or it could be easily swayed by the user's bias. Like, if you asked a heavily leading question, Guanaco was much more likely to just politely agree with you rather than accurately correct your false premise.
Got it, so it was a bit of a sycophant.
A bit, yes. But by explicitly showing us those lemons, they gave us a much more honest, three-dimensional picture of what this technology is. QLoRA makes the model incredibly accessible, and it makes it fantastic at following conversational instructions, but it doesn't magically cure the inherent underlying limitations of the base model. It doesn't turn a simple llama into an omniscient god. It just teaches the llama to talk very naturally, very, very efficiently.
And honestly, that builds so much more trust with the reader. It tells me, look, this technique is incredibly powerful, but it's not literal magic.
Right.
But I want to zoom out to the broader impact here, because reading this paper, it feels clear that this wasn't really just about building Guanaco. Guanaco was just the tech demo.
Oh, entirely. Guanaco was strictly the proof of concept. The real underlying product here was the methodology itself.
The so what of this paper feels absolutely massive.
Yeah.
Because before QLoRA dropped, there was this very genuine, very palpable fear in the community that advanced AI was going to be the exclusive lockdown property of maybe 3 or 4 megacorporations in Silicon Valley.
That was definitely the trajectory we were on. The moat was entirely based on hardware.
Yeah.
If you didn't have a spare $10 million for an H100 cluster, you just couldn't play the game. QLoRA completely broke that gate down.
Totally shifted the bottleneck.
It did. It conclusively proved that high-quality, state-of-the-art instruction following is entirely possible using off-the-shelf consumer hardware. It meant that a small university lab, a bootstrap startup, or even just a dedicated hobbyist in their basement could take a massive foundation model and fine-tune it to be world-class for their own specific narrow needs.
And the authors actually walked the walk on that. They released everything to the public.
Everything. They open-sourced the Guanaco model weights, all of the Python code, and critically, the highly optimized CUDA kernels they wrote specifically for the 4-bit training. They literally handed the community the keys to the car.
And we have seen the absolute explosion of innovation since then. I mean, if you go on Hugging Face today, there are tens of thousands of highly specific, fine-tuned models. You've got medical llama, coding llama, role-play llama. Most of those solely exist because techniques like QLoRA made them physically feasible for regular people to create.
Absolutely. It shifted the fundamental basis of competition. It changed it from who has the most raw capital to buy GPUs to who actually has the highest quality data set and who has the best, most creative ideas for how to use the model.
Which is exactly where we want the tech industry to be. Innovation should be driven by creativity and cleverness, not just hoarding capital.
I couldn't agree more.
So I want to leave you with a thought as we wrap this up. We started this deep dive talking about the David versus Goliath narrative in AI. If a single consumer GPU and just 24 hours of compute time can get you 99% of the way to the conversational performance of a multi-million-dollar data center trained model, what does that actually say about the defensive moat those massive tech companies think they have?
That is the big multi-billion-dollar question.
We naturally tend to assume that the company with the biggest pile of chips automatically wins the future. But QLoRA strongly suggests that maybe, just maybe, we are entering an era where raw brute force horsepower matters significantly less than the sheer cleverness of the software optimization. If you can elegantly compress the intelligence without losing it, do you really need the supercomputer at all?
It definitely suggests the gap between the corporate giants and the rest of the open source community is much, much smaller than the giants would like us to believe.
Definitely something to mull over the next time you watch a massive new model release event. That is it for this deep dive into QLoRA. Thank you so much for exploring this with us.
Thanks for having me.
See you next time.